Hello, this is Shakib Daryanoosh, and I'm going to present one of our latest results on quantum steering and dynamical quantum events. I've organized this video abstract in three sections. First, some background information to the content, then the statement of a no-go theorem for diffusive unravelings, and finally a quantum jump scheme that proves that the limitations imposed by this theorem can be evaded by using quantum jumps. The first quantitative dynamical model of quantum systems was given by Einstein, in which the system jumps between stationary states of Bohr. In this old theory of quantum jumps, dynamical events are independent of detection. However, in contrast, according to the modern theory of quantum jumps, measurements play an essential role, and as a result, dynamical quantum events are detector dependent. But one might ask, why should we care about the detection? Surely it is the emission of a photon that causes a quantum jump, and we would not need necessarily to detect the photon for a jump to occur. The reason this is not so is that there is not just one way of detection, and different detection schemes result in different types of jumps. Therefore, we do need to care about detection. Recently, an experimental test was proposed by Howard Wiseman and J. Gambetta to address the question of the title of their letter. The physical system here is a derivative two-level atom, and the key to this test is to implement two different ways of monitoring the emitted radiation, here X and Y homodyne, in which a strong local oscillator is added to system's output field prior to detection by a photoreceiver. This proposal disproves objectiveness of pure dynamical state by establishing EPR-steering. One of the outcomes of this work is that a necessary condition is that the detection efficiency should be larger than 50%. Now, having enough background, let's state our new no-go theorem. The no-go result of Wiseman-Gambetta applied to a system with one decoherence channel and two unravelings or measurement schemes. We have generalized these to an arbitrary number of decoherence channels and unravelings. That is, if an experimenter is able to implement m different measurement schemes on the l different reservoirs with which the system interacts, then as long as for all of these schemes and channels the efficiencies are less than or equal to 50%, it is not possible to establish dynamical EPR steerability. This no-go theorem would imply that detection schemes of measurements giving rise to quantum diffusion need improvement to be able to prove this detector dependency of dynamical quantum events. Here you see the latest experimental reports up to this date that at best they can have roughly 50% detection efficiency. In the last part, we showed that this limitation doesn't apply to quantum jumps. We consider a system with two decoherence channels to lower the threshold of detection required for EPR-steering. We make use of the concept of two-state physically realizable ensembles to keep track of the system. Here you see the block representation of such ensembles, with one in the z direction and an infinite number in azimuthal direction. To realize these ensembles, adaptive monitoring is implemented by adding a feedback-controlled weak local oscillator to the output field prior to detection by photon counter. To show detector dependency, we calculate a suitable steering inequality. It turns out that the critical efficiency would be 37% in the ideal case of many measurement settings, which is much less than 50%. This shows that no-go theorem is not universal. To have a fair comparison, we did calculations for diffusive unravelings, and it turns out that although the critical efficiency required to violate an EPR-steering inequality is less than the former proposal, namely 59% compared to 73%, but 59% is still far above the 37% efficiency we've shown is sufficient for quantum jumps. And therefore, that is why we say quantum jumps are more quantum than quantum diffusion.